Good afternoon, ladies and gentlemen. I'm delighted today to be joined by Dr. James Tour. I first came across James's work when I was in Jerusalem. I was visiting a family friend over there, and the gentleman came in from his work. He lectures at a local university, and he bounced in. He'd obviously had a good day. And he said he'd been at a wonderful lecture, a chap called Jimmy Tour. He looked at me and said, "Do you know Jimmy Tour?" And I said, "No, I've never heard of him." So, oh, it's great. So I mean, this was one academic, being enthusiastic about another. So I tried to feign interest, and I said, "Oh, what was he talking about?" He said, "Origin of life." Oh, I said, "What do they have to say about that?" So, he thought it was hilarious. He was such a good speaker, he had them in stitches. So I thought, okay, this sounds like someone I need to find out about. So I went away, thought, right, James Tour, Origin of Life. Let's see what I can find on the internet. So I started to find some lectures, and they were rather special. Just to give the audience a flavour of this, I have a little clip which we can play now, just of the nature of his, shall we say, commentary, criticism, critique of the mainstream in Origin of Life research.
Interactomes. This is the non-covalent interactions that function within a cell. Nobody knows how a viable cell emerges from massive combinatorial complexity of its molecular components. And of course, nobody's ever synthetically mimicked it. An interactome is the whole set of molecular interactions in a particular cell. If one merely considers protein-protein interaction combinations in just a single yeast cell, the result is an estimated 10 to the 79 billion combinations. That's estimated by these folks at Johns Hopkins and Brussels, all right? That's not my estimation. These are biophysicists, all right? So just to give you an idea of how big that number is, that's 10 to the 90th is the number of elemental particles in the universe. That's 10 to the 90th. This is 10 to the 79 billion. That's a big, big number. People do not understand numbers. They just don't. You say $1 million, $1 billion, what's the difference? $1 million or $1 billion? Well, let me put it in a way that you understand. 1 million seconds is 11 days. So you ask somebody, will you marry me? I'll tell you in 1 million seconds. Okay. If they say 1 billion seconds, that's 32 years. All right? You feel that now? 1 million to 1 billion? And then if they say 1 trillion seconds, that's 32,000 years. Huh? You see the difference when you go up 3 orders of magnitude? You go 1 million, 10 to the 6th, to 10 to the 9th, to 10 to the 12th. That's 10 to the 79 billion. That number's crazy big. That's just in a single yeast cell, the interactions between the non-bonded interactions. So how does the information flow? Information flows through non-bonded interactions through electrostatic potentials, which physicists call a virtual photon. Information goes down these at the speed of light. That depends on ordering between molecules, non-covalent interactions. These have to be all kind of assembled right. And that's why this information, you don't dehydrate cells and rehydrate them and get them to work properly. When a cell divides, it collapses down, puts the information on both halves and brings it into both sides. So that information keeps going to the next and the next generation. Because when you lose these intermolecular interactions that are non-covalent, non-attached, you've lost your information flow. Big problem. Nobody has explained. Nobody in Origin of Life ever mentions the word interactomes. Never will you hear it in their literature. Next slide. Proto-turkeys. Origin of Life protocell assembly is akin to buying 20 pounds of sliced turkey meat, adding a gallon of turkey broth, warming, sticking a few feathers, and suggesting that a live turkey will eventually come gobbling out. If given enough time, or that a proto-turkey or extant turkey has been synthesized. This is exactly what is done in Origin of Life experiments. Is exactly what is done. If given enough time, a turkey's going to come out. And people buy this stuff. There's a whole area of research called origin of life research, and they've been doing this same thing since 1952.
That gives our audience an idea of the nature of the sheer entertainment value on one level, and the level of knowledge that James Tour brings to this. Now, James, I'd like to start just briefly with a little bit of background, because you've got some unique insight into this whole area because of your day job, because of your scientific career, and what you've actually been doing by way of looking to create things on a molecular level. So could you give us a little overview of your scientific background before we get into your work as what you might term a public intellectual on this subject?
Okay, so I've studied organic chemistry now for 45 years. I got my PhD in organic chemistry probably 40 years ago, and working in this area, and I do a lot of research in this area, have a lot of publications, a large research group, a lot of patents, and this is what I do. I build molecules for a living, and this is not unique to me. Many people build molecules for a living, but what happens when you build molecules for a living, you know what they do and what they don't do. You know the kinds of reactions that they undergo. You know what parts of the molecules are going to react under what conditions. And people who have spent years in the laboratory building molecules have a very good understanding on how they react, and the things that they do and the things that they don't do. So that's kind of my background.
Just a little bit more on this. You were involved in creating a mechanical. Well, I think it was described as a little car, but it was a very little car that won a race. Could you just let us know about that?
Right. Oh, yeah. Okay. So you wanted a little bit about our research. So we've made nano cars. We were the first to make nano cars years before anyone else did. We were first to motorize a nano car. These are single molecule cars. They have 4 wheels, independently rotating axles, little motors in them. And you can shine a light, and the motor spins at 3 million rotations per second and pushes the car along a surface. We entered the first nano car race that was in France. We worked with a group in Belgium. We designed the car. We built the car. The group from Belgium raced the car, and we finished the race in an hour and a half. And the next group behind us was the Swiss group, and they came in 5 hours behind us. And none of the international groups finished the race after 30 hours. So we know how to build cars. These are so small you can park 50,000 of them across the diameter of a human hair. So we work in the synthesis of nano cars, nano machines. We've taken these little motors and we drill into cells to kill them. We've done a lot of work in killing cancer cells, killing superbacteria by drilling into the cells, tearing up the cell walls, and then just going right on in, or the cell membrane and going right on in and tearing up the innards of the cell. And we cause them to necrose, which means that they just blow out their innards very, very quickly. We work across a number of different areas. I've started over 12 companies, ranging from graphene, production of that single atomic layer of graphite, and we know how to build that from the bottom up. 100 milliseconds, which is 0.1 second, we can take any carbon material, any solid carbon material, turn it into graphene. That is in a company now called Universal Matter. They will be at a ton per day production of turning coal into graphene by this summer. I have 2 companies have become public. One works with graphene quantum dots, being able to extract from coal these particular graphene quantum dots that's used for anti-counterfeiting markings in high-end apparel like women's purses and shoes and many other things. I have another company that we've developed computer memory called Weebit, and they build computer memory that's all based on 2-terminal rather than 3-terminal memory, which is typical transistor. This is a resistive memory. It's based off of a silicon oxide, is what we worked on in our lab, and that's now a public company. We work on many materials projects, pharmaceutical projects, materials projects. electronics projects, and these are the types of areas that we work in. So we've had a lot of discoveries along the way.
Given that resume, all of those commercial successes and areas of interest, how was it that you became embroiled, probably embroiled is the right word, in the uncomfortable life of a public intellectual, showing up errors in mainstream science and taking all of the flack that goes with that? What made you move into that particular, somewhat thankless area?
One could say I was blissfully unaware that I was stepping into a minefield. I was challenged by a friend. I had attended a meeting that's put together by Peter Thiel, the founder of PayPal, and he has this meeting that some of us attend, and I heard some people speaking about evolution, and I was getting angry because some of the things that were being said I knew chemically could not happen. And then a friend of mine, David Berlinski, said, "Jim, why don't you write an article about this?" And so I started really digging into this and what the claims are. And I wanted to go back to the beginning, pre-evolution. What started this whole thing? And so there's this area called abiogenesis. I had never studied it before. And this is about 6 or 7 years ago, I suppose. And so I started reading about it. I started asking my colleagues. I asked my colleagues, how do they think carbohydrates were first made? How did these molecules start forming? And a friend of mine who's a very talented synthetic chemist, Casey Nicolau, who's here at the university, said, "Oh, these are made by the Foremost reaction." And so I started looking that up, and other colleagues started sending me some papers by a man named Albert Eschenmoser, the original work on the abiogenical routes to carbohydrates. And I read those, and it was a bunch of nonsense. It showed that this is absolutely how carbohydrates could not have been made. They're too messy. They don't give you the enantiomer compounds that you need. And it was just one paper after another by a litany of people that showed that this is how the chemistry could not have worked. Their own data screamed out, this could not be the way that these things had been made. So I wrote an article on it, and then I got a lot of feedback. I got an invitation to speak on this, so I would go and give a few lectures on this. And then I started getting attacked. Uh, and I didn't try to attack anybody. I was just attacking the work. But what was coming back at me were very personal attacks. That I was acting nefariously. That I was saying that people must be that people, anybody that would believe this is corrupt or stupid, uh, or, or or something like that. And I never said that. I never made an ad hominem attack against these people, as far as I know. And if one slipped out, I apologize. But their attack on me was never addressing my scientific claims. Never. It was addressing me personally. And so, here I found myself in a new minefield, but I wasn't backing down because I knew that I was in the right, and that eventually this is going to blow this area open, that these people, and it's not a lot of people, it's the Origin of Life community is actually a sort of a boutique industry. It's maybe a dozen people around the world, but they're really high profile people. And what's happened is whatever they come up with, the press ramps it up an order of magnitude. So they ramp it up, and then the press ramps it up even more, and it gets into our textbooks. And this is what our young people are learning, so that the primordial soup model, that in some pool somewhere these molecules started forming, and then they came together and formed a cell, and then higher order structures, and that's how you got life. That's primordial soup model. That model is not just in elementary school textbook, not just in high school textbooks. This runs right up into college and upper level college textbooks, this primordial soup model, and there's no basis for it. There's nothing there. There is nothing there. So I figured I'm just going to talk about the chemistry. That's all I know is chemistry, and so I'll talk about it.
I mean, I remember maybe high school, right? The primordial soup model was discussed, and this was all there was. So how did life start? Well, we don't really know, but we had the primordial soup hanging around looking soup-like, and there was lots of chemicals in it. And there's a power source, lightning's normally offered. And then we had the first amino acids, and a particular experiment was pointed to that gave some justification for that, although there were some issues. And then, well, they assembled and formed the first cell, and life continued from there. And it was all a bit, well, vague is putting it generously. That was high school quite a number of years ago, decades ago. What is the cutting edge of origin of life research now? What is, you said it's still the primordial soup model. Has it got any more refined? Is that still the state of the art? What is the official top level science best word on the subject today?
So my constant cry has been that very little has been done since the Miller-Urey experiment in the 1950s, to which you refer, where they took some small molecules and they put high voltages across it to try to simulate lightning, and they got the formation of several of the amino acids. Now, all of those amino acids were racemic, meaning that they had both the left-handed and the right-handed structures. You have to have non-racemic amino acids, meaning that you have to have just one-handedness. We have no idea how the world dealt with that, how the Earth dealt with that. Now, there are only two of so you have 20 amino acids, 19 of them have stereogenic centers, which means 19 of them can be handed. Of the 19, two can crystallize such that they they can be enantiopure, but then you have the other 17 that don't do that. People have said, well, those other 17 can co-crystallize with the other ones in pure form. And then when you look at the very papers, they'll co-crystallize in less than 1%. So the vast majority of the material is still racemic. Now, I know this is a bunch of scientific talk to a lot of people that don't know chemistry, and I'm not trying to move it into such a scientific talk that people wouldn't understand. But what I'm saying is the models just don't work. Everything we know to date screams out that this could not have been the system to give us the enantiopure systems that we are going to need. The problem is much harder when we go from amino acids to the carbohydrates, or sugars they're called. The carbohydrate, sugar, saccharide, that's all the same thing. That's three names for the same thing. When you go to that class of compounds, the complexity gets much, much harder. But so you have the four basic building blocks, which are the amino acids, which you mentioned, and then there's the carbohydrates, the second class. That second class is deep hard to think of how that put together in any prebiotic sense. So we're stuck on that too. Then the next class is you have the nucleic acids, which are the DNA and the RNA. For DNA and RNA, you first have to have one of the sugars, ribose, or a derivative of one of those sugars, deoxyribose for DNA. And then you have to be able to put on a base. Making the base is easy. That's not hard. But putting on the base onto the fructose, onto the ribose, and then taking that and putting on a triphosphate, putting on a phosphate to make it into a nucleotide ready for polymerization is very hard to do in any random sense. And then getting these hooked together is a whole nother problem. How do you get the amino acids to hook together to form proteins and enzymes? We don't know how to do that. You can get very small amounts of coupling. If you dry out the system, if you can dry it out in sort of a small droplet, sort of like the recent Purdue experiment. But all of these are loaded systems. They don't use the functionalized, the active side chain amino acids. So everything is loaded. They stack the deck on all their experiments, even the recent Purdue experiments, all stacked. They don't use any of the active side chain amino acids. Now you're stuck. Half of the amino acids have active side chains. Those participate and screw up the chemistry. The carbohydrates, nobody knows how those hook together. So now, because I've been attacking them on this, they concede, yeah, it had to have been enzymes that put that together. Okay, so if it was enzymes that put carbohydrates together, who put the enzymes together? How did you get the enzymes to hook up when you had unprotected side chains? They're stuck. And now, when you have the nucleotides, how do you get the nucleotides to polymerize to get RNA to polymerize so that it hooks together rightly. It doesn't. It hooks together wrongly over and over again. It hooks together in the wrong way, even if you had the enantiomer form. And then the last of the 4 types of compounds are the lipids. People think the lipids are easy. No, they are very hard. It is very hard. Every protocell experiment has done this wrong. The chemistry itself screams out that these steps do not work. And so that's been the problem about the whole thing. I hope I didn't take it too far afield in the chemistry.
No, that was ideal. I've occasionally, and I do try and avoid this because it's horrible, got sucked into debates on Twitter and other public communication platforms on the whole subject of theory of evolution. And it's a very strange thing because it seems to have a little bodyguard of people around the idea. And if you say anything against it, there's an immediate pile-on of a gang of very aggressive people telling you how stupid you are. And there doesn't seem to be any interest in any of the issues. The issues that the sort of thing that I would tend to raise would be ones to do with the mathematical probability of any of this stuff happening, and also just the sheer complexity. I mean, I know very little about this. I've read a little bit. I've read some stuff from Behe. I've read some stuff on the what a cell is. And it's astonishing to me. It's this factory, and it deals with waste and deals with manufacturing, and it subdivides. And you're looking at this is phenomenally complicated. Where does the information come from? How the information to create that we couldn't create now. How did it ever arise? So there's that, and there's also what's the first building block, right? Because back in the days when I was a lad and this was being taught to me, you had the first amino acids, and then they would assemble themselves into eventually a simple cell. So there's 3 issues there I'd like you to just touch on. 1 is the mathematical probability of this. 2 is how simple is a simple cell? How simple can a simple cell be? And the third one is the issue of information storage. So I know that's a long compound question, but could you just briefly look at these 3 issues and give us a bit of insight as to the nature of the problems that lie therein?
There is no such thing as a simple cell. Every cell is amazingly complex, but this has been calculated. So you can use calculations to figure out how simple a cell could be in order to have life. I've not done the calculation. This was done by biophysicists. So they have figured this out, and they give the pieces that are needed to build a simple cell. So it's about 15 different pieces you would need to build for there to be a simple cellular life. Of those 15 pieces, zero have been made by origin of life researchers, even in their laboratories, even with all their equipment. I'm not talking about under a rock or in some pool by the side of the ocean. I'm talking in their pristine laboratories, building up these molecules and making any of those 15 pieces. You have to have the whole transcription machinery, the whole translation machinery. You have to have DNA repair, restriction. You have to have each one of these pieces. None of them, 0 of them have been made. Some will say, well, at least we can make the outer vesicle area, the lipid bilayer. You cannot. It is not just a simple vesicle where the inner and outer layers of the lipid bilayer are the same. All protocell experiments have those the same. You just take a diacetyl lipid and you put it under shear, meaning you rub it together and in water, and you will get some of these what are called vesicles, which are these containers, these spherical-like containers that look like a cell membrane. But they're very different than a cell membrane because we only know how to do this where the inner and outer layers are the same. In a cell, the inner and outer layers have to be different They have to be different to maintain what's called a proton gradient, a difference between the outside and the inside. And this is what allows for life. And the way that's done chemically is you have saturated systems on the outside, unsaturated systems on the inside. We know how biology does this. Life does this with something called flipase enzymes, enzymes that are able to construct in that way. We have no idea how to do this in our own laboratories mechanically to set this thing up, chemically to set it up. We can't even make the proper protocell outside. Mathematically, any mathematician that looks at this saying, what are the mathematical possibilities of being able to form life? You're dead. It's just dead. You can't even begin. The numbers are so astronomically against you. And those numbers don't even deal with all the issues. The video that you were showing talked about the interactomes. The interactome problem, just the non-covalent interactions of what I was showing in that little introductory video that you had was in a simple yeast cell. A yeast cell is a very simple cell compared to, say, a mammalian cell. In that simple yeast cell, the number of combinations of just the protein-protein interactions was 10 to the 79 billion. That's a 10 with an exponent of 79 billion. The number of elemental particles in the entire universe is 10 to the 90. 10 to the 90. So we got 10 to the 90 versus 10 to the 79 billion. This is crazy different numbers. These are numbers that suggest we have no idea how these get arranged in the proper order, how this happens. So mathematically against you, it's against you. Chemically, it's against you. And then you look at the structure of the simplest of cells, because the origin of life researchers will say, well, the cells were much simpler back then. We already know how simple a cell could be to operate. That's already been calculated. And we've made zero of the structures humans have made, let alone under a rock somewhere. So we can't even get evolution going. Before evolution can happen, we've got to have the first life. Once we start getting this going, now keeping it going is really hard. People thought we didn't have to control the handedness of the molecule, the molecular shape, the handedness, whether the left hand or the right hand, and that those evolved later on as life got more proficient. We now know, because of work coming out of the Weizmann Institute by Ron Naumann's group, that you had to have near perfect enantiopure materials at the start of life. How that ever happened, we have no idea. You can't even get life going, because if you don't have enantiopure materials, everything burns up. The chemistry generates too much heat for the cell to ever survive, because you get backscattering of electrons. These are spin valves. This is how natural systems operate. So we can't even get it going. We can't start evolution. So why even really discuss much about it? We can't even start it till we have the first cell. We can't even make the first cell. Now, within the area of evolution, there's lots of problems. You can make small modifications. We do these small modifications in my lab all the time. These we do with bacteria in my lab. We work on killing superbacteria. So we make bacteria, and we make it more resistant by bringing it through generation after generation to try to see what are the ones that the antibiotics cannot kill, and then show that our little nanomachines can kill them. This is what we do in my lab. So we understand things about this. It's not like this is a total black box to me. We do this work in my lab. We've published in these areas. And so what happens is you can make small modifications, but that bacterium always stays a bacterium. It doesn't change into something else. There is no understanding of how many changes are going to be needed to change one system into another. People will say the immune system morphs. It does. It's constantly morphing, because this is the way the thing operates. But the immune system remains an immune system. It doesn't turn into an auditory system for your ears, or an optical system for your eyes, or a digestive system for you. It remains an immune system. In order to have system level changes, the number of changes have to be so many, we can't even figure out how to do this ourselves, let alone how this would happen in a naturally occurring way. So evolution has its own set of problems, but I generally don't even deal with that, because I'm just stuck on how did you get life going in the first place.
The scientific world has no idea how life started, no viable mechanism for making it happen, even in a lab. That's not the public perception, though, is it? The public perception is a bit vague, but it's much more positive than that. The public has a perception that either this has been achieved, or it's on the brink of being achieved, or it's certainly that it's understood. I mean, I think this is a really important little data point, that science does not have a clue how life started, and isn't, well, it's not even that it isn't close to unraveling this. It's actually getting further away, because the complexity of the cell is so much more than it was understood to be 25, 30 years ago. So the minimum starting point is actually getting further away. What do you make of the public understanding of these? Are you lecturing a lot? You're lecturing to the public. You're lecturing not just within the scientific community. And then you're going on YouTube and you're lecturing there. So you must get a lot of feedback from the public. What's your view as to the public understanding of this? How accurate it is or isn't?
Okay, so let me just take a step back. If we have a cell and that cell just dies, so everything, all the compounds are there. Everything is there and they're in place. They're all assembled. Because even if I gave you all the compounds, nobody knows how to assemble a cell. Nobody's ever done it. But even if we have a cell that just died, so the assembly, we don't know how to bring it back to life. But it's more than that. We don't even know how to define what it is that we just lost. We can tell you that we've lost proton gradient changes are lost. We can tell you of different structures that it's no longer in homeostasis, that there's no longer metabolism. We can tell you features about what we've lost. But to define life, the actual thing that we just lost, we can't even define that. That's how bad it is. Now, getting back to your question, the poor lay public is so misled on this. And the problem is the origin of life researchers themselves make these crazy bold claims, and then they share it with the press, and the press ramps it up and makes many more crazy bold claims. These end up in our science textbooks, and the lay public is greatly deceived. So John Narcombe took a survey, and he said, is it true or false that scientists have made simple organisms like frogs in their laboratory from basic building blocks of chemicals? And 1/3 of the public, 1/3 of the general public thought that that was true. Then he backed up with another question. He said, do you think it's true or false that scientists have taken basic chemicals, put them together to form something as simple as a single cell, like a bacterium? 2/3 of the public thought that was true. The answer to both of those are false. Now, 80% of the people who took that survey, and it was like 750 people took the survey, something like that, 80% of them have some type of college degree ranging from 2-year to PhD degree. And so 2/3 of them thought that they had made frogs. 1/3 of them thought they had made simple cells. Both of those are false. We've not even made the basic building blocks to be able to try build a simple cell. And even if given all the building blocks, we wouldn't know how to make it. And getting back to your former question, the information, the code for how this thing operates, the information, we have no idea how that happened. People will say, well, you happened to get a strand of RNA that had the code because you're going to have some arrangement and that happened to form the right code. Well, that strand of RNA, if you have just one strand, is not going to be very stable. That will be, you won't even have hours to use that before that one strand, because we're not talking about what is the half-life of a mole of compounds, 6 times 10 to the 23rd molecules. We're talking about the lifetime of a single molecule in water. So you don't have the time. The time is against you in this. So this is how clueless we are, and the poor lay public has been greatly deceived on this. And if you try to bring clarity to this, this is where the attack comes from.
Yes, and you mentioned time there, because time's generally painted this is the solution. Right? What this doesn't seem to add up. The probabilities are astronomical. The response is, well, billions of years. You get lots of goes in billions of years. So time, very long periods of time, are held to be the solution to all of these questions. And is that how you see it?
No, time is actually your enemy. When you're doing organic synthesis, time is your enemy. You have molecules. The very reactions that make carbohydrates, the foremost reaction that makes carbohydrates, the very sugars that you want decompose under those reaction conditions. So what a chemist has to do is they monitor these reactions and they watch when the yield for the compound they want is optimized, and they right away quench the reaction and fish out what they want, because it goes bad. The reactions go bad. They go bad very quickly under the very reaction conditions in which they form. They go bad. It's like baking a cake. I mean, if you take the cake out at the right time, if there is an operator there that can remove that cake or remove that apple pie from the oven at the right time, you're good to go. It's fine. But if you don't have an operator there and you just say, well, just let it go, it'll be all right. I mean, that apple pie doesn't taste very good, even if you leave it a few minutes too long. And so time is really your enemy under the very reaction conditions in which these form. So every origin of life experiment just stops it at the perfectly right time. The operator is there to stop it at the right time, or you get utter junk. Time is your enemy. Time causes decomposition. And even if you had the right molecule outside of the reaction conditions in which it formed, then oxygen from the air will cause these to oxidize over time. If you say that the earth back then was more reducing, all right, so it had more ammonia in the air. Ammonia is more reducing, more reactive to organic compounds than is oxygen. And so these things decompose. And this is why, I don't know if you remember this, but the older cars, the dashboards on the cars, after 4, 5, 6, 7, 8 years, they would be totally cracked. And that's because of the oxidative and light-based, the UV light ray decomposition, and the tires would be totally cracked. And now they just fill them up with these things called antioxidants to slow this thing down so they don't crack so quickly. But you see this all the time, an old rubber band, you stretch it to try to use it, and boom, the thing just breaks in your hand. Why? Because the molecules have oxidized. They've cross-linked in there due to these radicals that form through oxidation in the air. These things go bad. They don't last very long. So time actually becomes your enemy when these people think that time is your savior. Time is your enemy when you're building organic compounds.
Now, you mentioned there briefly about being attacked. Now, I've watched a good number of your lectures and presentations, and you're a very nice human being, right? You're very gentle. You say how you're very careful. You don't want to attack anyone personally. You don't want to go do any ad hominem attacks. Right? Now, I'm a bit more of the Murray Rothbard school, where an ad hominem attack is a logical fallacy. It doesn't refute the argument. So first you refute the argument, then you go for the man, right? But you're much nicer than me, right? And I've watched you do this, and you've been very careful, and you've been very nice and very precise, and you're looking at the information, and you're careful not to attack anyone personally, right? And I go on, I was looking at one of your videos not so long ago, and you're saying, I'm locked and loaded, right? You say, anyone who goes on one of these shows attacking me, any scientist, I'm coming after his work. Not him personally, but I'm coming after his work. And I'm thinking, oh, they've pushed this man too far. Have they?
Yeah, they pushed me too far in the sense that I'm going after their work. I will absolutely go after their work. And, it's not that I don't feel the ad hominem attacks that come against me, but because I love the Lord Jesus Christ, I have to live by a different standard. I'm called to a higher standard. And so, but I can just deal with the science, and they go on these programs and they start talking about their science. So what's happened is they have these researchers have gone onto a social medium. They've used social media to try to get out their message, and they've used social media now to go out and try to attack my message. So I will go right after them using the same medium. You've come on in a social medium to come after my work. I'm going to use the social medium to go after your work. Many people ask me, why don't you write papers on origin of life? I've written 5 papers on origin of life. That's 5 more papers than most people have ever written on the topic. Um, I've published over 750 academic research papers. So I really know how to publish papers. But I'm not trying to go after the scientific community in that medium because many people, I'm not the only one. Clemens Reichert, Shapiro, many people, many scientists have gone after the very origin of life science that we're talking about in the scientific literature, and these guys ignore it. They ignore it. So why should I write papers that people are going to ignore? I've written papers on it. They ignore it. They never address the problems that I'm talking about. So I'm going to go right to the masses because the masses do not read scientific articles. People who generally are watching YouTube videos on this are not reading the scientific articles. So I'm going to use that medium and go right after them using that medium. And when I said I was locked and loaded, that just means I'm ready. I'm ready to go. And I'm going to go right after these guys. And if you've seen some of my recent videos, that's exactly what I'm doing. I'm going right after their science and I'm tearing it apart. And I'm going right after their claims. And I'm going right after the things that they say and comparing it head to head with the things that I say so they can see what these people are doing. I say one thing and then they get on a video and they say, Jim Tour says this. I said black and they get on a video and they say, Jim Tour says white. And I show them so the world can see, what did Jim Tour say? What are they saying that I said? And then I go right after their work. That's exactly what I'm doing. I'm going to use that social media. In fact, my first series, which was a 14-part series, it had about 10 hours of content. I didn't use any memes. I didn't use anything, and it's actually quite boring. I mean, if you really want to get the hard guts of Origin of Life, listen to that 14-part series, which I now have like in a 9 or 10 hour value pack series that you could just click once and just watch the whole thing. If you want to have a serious demonstration on the problems and origin of life without any memes, you go ahead and just watch that. That's for you. But I'm now trying to go after another generation. I'm going after a generation of people that will not watch that 14-part series because it's just dry science, one thing after another, dry science, talking science. They don't like to watch that because they're not scientists. So it's very hard for them to get through that. Only the serious student can get through that 14-part series. I don't blame them. I even said in there that this series can be a cure for insomnia because there's just a whole lot of scientific content in here. So now the series that I'm coming out with, working with a good production team without the ad hominem attack, but I'm just putting some memes in there to break it up and make it a little bit silly in between the content. There is solid content there in the science, putting in the memes there to show the ridiculousness of what these people are doing because I'm going now after a different generation. And this is the way that I'm bringing it forth. And then Christians come against me because they say, oh, you really shouldn't do this. You shouldn't do this. Everything from don't even go back. The Christian thing would be not to even respond, or at least do it without the memes. And I'm like, no, why don't you read about what Jesus said? He said to the Pharisees, you are whitewashed tombs. You talk about ad hominem attack. He told them they're whitewashed tombs. John the Baptist said to the Pharisees, the religious leaders who were coming out, he said, you brood of vipers. Jesus called one of the Herods, one of the Herod's sons, he called him a fox. I mean, so if you look at the things and the way that these people called people out, I'm actually quite nice relative to the way the Bible gives me freedom in the New Testament to call people out. I'm actually being quite nice. So that's what I'm doing, and I'm trying to reach a new audience here to get this word out because this audience is not reading the academic papers. This audience wants to get content, but they can't listen to 9-10 hours of content and put you to sleep. Put anybody to sleep, unless you really love organic chemistry, unless you're really a serious student and you're going to have to be tested on this. But other people, they want a little bit of humor in here, just mixed in, And it just shows the ridiculousness of the claims of these people. And that's what I'm going to do. So go ahead. I invite Origin of Life researchers to go on these YouTubers' channels and talk about all their research. Every paper you bring up, I'm going to look at that paper. I'm going to look at the experimental, and I'm going to show directly from that paper how it screams out this could not have been a mechanism by which life started. This could not have been. Every paper that they cite, every paper I'm going after. Because in my first series, I talked about different papers and I was accused of cherry picking. All right. Every paper you put on there, I will go after. You choose the paper and I'll go after it. I'll look at the supplemental, something that you don't have the ability. Most people don't have the ability to study. In the supplemental, it gives all the details of exactly how the experiment was run. They have to, if they've published a proper paper, it has to have all of this experimental supplemental data. And this is what I'll do, and this is how I'll go after it.
Okay, well, just to close, one final question to close. You've described beautifully the problem, not only with the science, but the problem with the reaction to questioning. But this is not new. An English physicist called Herbert Dingle was questioning Albert Einstein's work. And he came up with a question and he wanted the question answered. And he tried and he tried and he tried through all of the formal processes. And he was president of the Royal Astronomical Society. So he wasn't a minor player. He was part of the scientific establishment. And he could not get the question addressed. So he eventually went to the equivalent of YouTube in the 1960s, which was the Listener magazine, a fairly intellectual but for the public magazine. And he had letters published in there. And there was a bit of exchange, and then it was closed down. And he had a question, he said, give me the answer to the question. If you've got an answer, give me the answer. And the closest he ever got to someone actually answering the question was a scientist who said, well, your mistake is so obvious, it's beneath my dignity to answer it. They said, no, please, I've been at this for 25 years. I've been asking this question for 25 years. You know why I'm wrong. Tell me. No. And he never got an answer. He couldn't get an answer. And he found there was a fundamental problem in the scientific world because it was split between the mathematicians and the experimenters. And the experimenters didn't understand the mathematics. And the mathematicians were going down routes which were theoretically interesting on a mathematical basis, but didn't necessarily have any physical reality at all. And the two areas had become separate. And there was no integration, there was no coherency, there was no substantial reasoning going on. It was this very rarefied mathematical analysis, and everyone just assumed that the mathematical physicists were doing that right because no one could understand what it was. And then the experimenters would come along later and kind of experiment where they were told that something would be and not really find anything. And nobody addressed the growing problem. So my final question is this. You've come at this from, not from a line of physics, but from organic chemistry and synthetic organic chemistry, and you've gone into Origin of Life, and you've even had a little bit of exposure to the wonderful world of debating evolution and asking questions about that. Do you see this as a bigger problem? Is it a bigger problem in science? And if you do see a bigger problem in science, have you managed to put into words at all what it is?
Yes, I mean, scientists are like anybody else. We want to protect our areas. We want to defend our areas. And I understand the pain of these folks in the area of Origin of Life. They have spent their careers, they have spent 40 years proclaiming something on Origin of Life. And I come along and I start saying it's a bunch of nonsense. So I understand how that would affect them. But instead of addressing my science, it's actually very much like the story that you told. They're trying to go after me personally, or they're saying that I said things that I never said, and they're not addressing the scientific questions. None of them will address the question of interactomes. None of them will address the question of chiral-induced spin selectivity, which we have to have that's necessary. None of them want to even face these sorts of things. None of them will address the question of having a lipid bilayer where the outside and the inside layers are different. They won't address these questions, and that's why it's very much like Lord Kelvin says. When you come with a radical new theory, the people who work in that area, the only way to have success is to wait until they die, to wait until they die. And that's why I say that all origin of life researchers will die before we find the solution to this problem. All origin of life researchers' students will die before we find the answers to this problem, just because we are very far from having the solution, something you said before. But I have said numerous times on the internet, on my own YouTube channel, which, by the way, is Dr. James Tour. Dr. James Tour is my YouTube channel. I have said numerous times, I suspect one day we will find out how life originated, the scientific basis upon which life originated. Just like we found out in the 1950s how information is stored in the cell, in the DNA, when Watson and Crick came up with that model. And their coming up with the model didn't make God less. It just made it just more magnanimous in our eyes that, oh, that's the way you did it. So I suspect one day we will have a solution to that, to the origin of life. But that day is far from today, because every piece of information that we learn about a cell makes the cell more complex, not because the cell became more complex, but we just didn't know about it before. It makes the target more complex. So it's very far away. So the scientific establishment, there is an establishment here, and people don't want to change the views because they've been propagating these views all their lives. So I can understand how it's hard to say, wow, maybe I had this thing totally wrong. I was wrong on all this. All those papers I published, I was wrong. That is a hard thing to receive. I mean, scientists are like anybody else. We have these fears, and we want to allay our fears. We don't want our things to come crashing down. But in something like this, it's gotten so out of hand that all of our textbooks are wrong, and all of our understanding from these surveys are just so wrong that we've so confused the people. This has got to be addressed. So yeah, there's a problem with science, but it's so good that we have now social media where we can take this message out, and they'll say, well, why don't you just publish papers? Because I have. Other people have. Nobody's listening. So we're now going to take it to the masses. Scientists have bemoaned for many years, chemists have bemoaned the fact that the world doesn't listen to chemists. They don't really know what's going on in our field. Well, we're getting the word out there now through a social platform. That's a good thing. That's a good thing, something that we've been striving to do with all these expensive outreach programs, trying to go into schools and touch little minds and touch little hearts with chemistry so that we can get them excited. How about this? We're going right into the masses, right into their living rooms and their dining rooms and their kitchens and their bedrooms with this social media platform, and we're taking chemistry to the masses in this way. There's a lot of young people that are getting excited about chemistry hearing this. And so we're going to expose this. In the process, we'll expose the problems in science. In the process, we'll expose the problems with these researchers' work. And in the process, we will get young people excited about science and what you can do with science. So I think this is all good.
James, thank you very much. It's been a real pleasure. Thank you also for mentioning Lord Kelvin. When I was many years ago at Glasgow University, I parked the car in Kelvin Way and passed his statue every morning as I walked in. So there are happy memories there as well. Thank you for your time today. It's been a pleasure listening to you. Until next time, thank you for all your efforts, and we will continue to watch your work with great interest.